Hey, what's up, guys? Yeah, so today I want to talk about this schwarz lemma in complex analysis. So this theorem is it's like a little bit advanced one. So usually you will not heard about it in the undergraduate complex analysis. But once you have this powerful technique, then you can use this to solve more difficult problems. Okay, and if you want to see more complex analysis video, that you can check out my list below. I hope you guys subscribe to my channel. Okay, so recall that in previous in a complex analysis, there's an idea called the maximum modulus theorem. So this theorem tells you that the holomorphic function, so f of z is holomorphic, so holomorphic function, and has a maximum or minimum and boundary unless f of z is a constant. Okay, so this maximum and minimum are both for both global and the local. And the proof is just using the Cauchy theorem. Okay, so so this tells me that this can give you very simple results of the following. So this is a theorem. This theorem says that let's give some notation. Let's say D10 is all the z belongs to complex plane, such that z is less than 1, and the D10 bar is the closure, so z belongs to C. Z less or equal to 1. And then our assumption is that f of z is holomorphic. So f of z is holomorphic on D10. Okay. Okay, so by let me just write down. So we have, so let's write down theorem. So theorem says that if f of z so our condition is that if f of z less than 1 when z equals to 1, so that means you have a bound on this on the unit disk, on the boundary unit disk, then you will have f of z what? So by modular theorem, boundary can only happen, maximum only happen on boundary. So this guy less than 1 when z less or equal to 1. Okay, so this is a trick. You start from here, change here. Okay, so this is the first. So this is the third for first, and second is that the same condition. The same condition is that if f of z less than 1 when z less than 1, sorry, it's not if. So if this condition holds, that it means that there is two possibilities. One is that f of z less than 1 when z less than 1, because by modulus principle, unless f of z is a constant. So f of z is constant. Okay, so this theorem tells you that if this condition holds, then you can say this, and more detail that you can say either one of these must be true. Okay, so once we have this, then we can say that we can start to go to the schwarz lemma. Okay, so lemma, there's another lemma, which is okay, so suppose f of z is 1, and when z equals 1, so f of z's boundary is exactly 1 and z equals 1. If f of z is non-constant, then there's a z0 belongs to the unit disk, it belongs in a disk, such that f of z0 is 0. Okay. Oh, so this is weird, right? It still tell you that if you have a function, if your boundary at 1, if you have a function which is has the modulus 1 on the unit disk, and it's non-constant, then you can always find the roots inside the disk. Okay, it's a proof. Okay, so by previous results, right, by this maximum modulus, we will have, so it's non-constant, right? So we always have f of z less than 1 when z less than 1. Okay, so once we have this, and suppose that there is no z0, then so suppose there is no z0, then 1 over f of z is analytic, right? Simple fact, 1 over f of z is analytic, and then if you do 1 over f of z, then you get this. You also get 1, right? Okay, then by the same thing, you do the second time, you do the maximum modulus. You also do the same thing for 1 over f of z. Then you will get what? Then you will get 1 over f of z is less than 1 when z less than 1. And then you can see that these two, okay, contradicts to each other. Okay, so that means our assumption is false. There should be a point which f of z0 is 0. Okay, for example, you can consider f of z to be z to the n, which satisfies this condition. Okay, so now we are able to go to this Schwarz lemma. So let me just write down Schwarz lemma. Okay, so the same condition, f of z is analytic. So this is our assumption. And take d0, d10, and f of z less or equal to 1 for z less than 1. So you do the same thing. Okay, so this theorem tells you that if, so these are our condition. If f of 0 is 0, then f of z less or equal to z for all z less than 1, and the derivative f0 prime is less or equal to 1. Okay, so the first one. Second one tell you that if f prime of 0 is 1, or f of z is exactly the same as z for some z. So this tells you that if f prime of 0 is 1, or f of z equals d for some z, then we always have f of z equals to its linear cz. C is 1. Okay, so this function, this tells you that if your function, if you have this condition and your f0 is 0, then f of z is bounded by z. Okay, and the derivative is less or equal to 1. So this tells you that this function cannot be cannot have much restriction. But if you also require that the derivative at 0 is 1, or f of z equals d for some z, then this will force this function must be linear. Okay, so this is the Schwarz lemma. Okay, so proof is very simple. So since we all have all the power, right? We have all the machinery. So proof is very simple. If z is less than 1, and let's say, okay. So yeah. So now let's consider this g of z. So obviously that you can see that g is analytic under at the region d10. So which means that so let me just write down. So first we know that for every r less than 1, if z equals to r, then your g of z is f of z divided by z is less or equal to 1 over r, right? Because by my assumption that is this f of z is less or equal to 1. So this tells you that it's less or equal to 1 over r. Okay, so by maximum modulus theorem, tell me what? Tell me that I just copy, right? So I just copy this. So g of z less or equal to 1 over r if z less or equal to r. So change this to this. Okay. Okay, so now this is for r less than 1, right? So r can be abstractly, r can be absolutely or however close to 1. Okay, so you can take r approach to 1. Obviously that you will get g of z. So g of z less or equal to 1 if z less or equal to 1. Oh, sorry, less than 1. Okay, you can try to prove this is true. This is not difficult. You just make r approach to 1, because r will approach to 1 arbitrarily close. So if you approach r to be 1, then g of z must less equal to 1 if z less than 1. Okay. Okay, so so what? Okay, so this tells you that this. So if g of z is 1, for some z less than 1, then this means that by the modulus theorem, then this g of z is constant. Okay, so g of z is constant. Okay, so this means that this means either this guy, either so this means that f of 0 is 1 because it's the modulus is 1, right? Or f of z is exactly the same thing as z. Okay. Okay, and so finally my Beck's module, because you're okay. So now let me just explain what is going on. So if f prime 0 is 1 and the g of z is constant, this tell you what? This tell you that by this you will get what? You will get the g of z is c. G of z is constant. So which tell you that f of z is just cz. Okay. Okay. So obviously that this will give you c equals 1. Okay. I think this is a proof. Okay. Okay, so let me just quickly review the idea. Okay, so for every r less, so up to here, we proved that g of z is less or equal to 1 if z less than 1. Okay, by this theorem, we basically proved up to now we proved this is true, right? And we proved this is true. And then we also proved that every prime less than 1. So because this is proved by using g of z. Okay. And then f of 0 equals to 0, I think what we have used is here, because we want to, if f of z is 0 is 0, then I can show, then we can show that g of z is analytic. So from this black box, we already proved this one is true. We already proved this one is true. Okay, so if f prime is 0 or f of z equals to z, then the will make maximum modulus to be true. Then once this to be true, then g of z will be a constant. Then we'll force g of z to be constant, f of z will be cz, c must be 1. Okay, so idea is that, okay, yeah, this is a proof. Hope you guys understand. Okay, so there's an application I think is also interesting. So let me just highlight this application. Okay, so this is called the bianalytic map on D10. Okay, so assume f of z is 1 to 1, 1 1 on 1 1 of D1, not 1 1 on 2, D1 0, on 2, D1 0. So it's 1 1, so it's bianalytic, right? So these guys 1 1 on 2, and also f and f inverse is both analytic. And we want to say that how many, what is such kind of function. Okay, so theorem tell you that if f of 0 is 0, so this is condition. If f of 0 is 0, then this function must be what? Linear, right? By guess, right? So that's not linear. So if f of 0 is 0, then this function should be linear. Right? So this is your guess. Then turn out to be correct. CZ. Okay. And the C should be 1. And now let's go to proof. Okay, so let's hope it's clear. Use this, and we want to prove this. Okay, it's not difficult by using the schwarz lemma. Oh, there's no T. Okay, so lemma. Okay, so this schwarz lemma on f of z, and its inverse. Okay, so by previous schwarz lemma, we want to show that we need to use f of z less or equal to 1, and for z less than 1, and we can talk about something, right? So by let me just tell you. So by Schwarz lemma, we want to use this. Or maybe also use this. Okay. So we know that the f of 0 is 0, right? Our construction. So we know that the f of prime 0 is less or equal to 1. This is by Schwarz lemma. And also f of inverse 0 is 0. So we also have f inverse of 0 prime is less or equal to 1. Okay. And so second, we have f inverse z equals z. So we do a differential. So we get f prime of 0, which is chain rule. F inverse 0 is 1. Okay, so from here we know that what? We know that what? We know that we know that these two guy times should be 1. Okay, but one of it is less than or equal to 1, and this is less than or equal to 1, but their product's 1. Okay, so combine these 3. What we have is what? Both are 1. Okay, because you have two number which is absolutely less than or equal to 1, but their product is 1. So which will force a prime of 0 is 1. Okay, and so by Schwarz, if f prime 0 is 1, that means that f of z is cz, with c less than equals to 1. Okay. Yeah, so this is the proof. Okay, and notice that this 1, 1, 2 is very important. So 1, 1, 2 is very important. Okay, otherwise you can choose f of z to be z squared. Okay, so then the results will fail. So 1, 1, 2 is very important, because once 1, 1, 2 is correct, then we can define its inverse, and then we can do the chain rule. Okay, so this is the proof. Or once we have this Schwarz lemma, then we can prove more difficult theorem in the complex analysis. Okay, so hope you guys subscribe. I hope you guys like this video and subscribe to our channel.